right, so, well, there's no evidence that ants that large ever existed, or that large. There is fossil evidence that insects got pretty big back in the Carboniferous era, around 258 to 398 million years ago. And ants got as big as hummingbirds, about 2 inches. And dragonflies, there are fossil records that dragonflies are as big as hawks, with a 6 feet wingspan. And there's a lot of hypotheses out there as of why they were able to be that big at that point in time and why we don't see insects that big now. And there are a couple of, so I'm just going to talk briefly about a couple of hypotheses. One of them has to do with the exoskeleton of the insect. So the idea is that the exoskeleton, the sheds for the animal, for the ant to grow. And as the ant is shedding, it's vulnerable to attacks from predators. And as they get bigger, they're more conspicuous, they can't hide, so they're even more vulnerable for being a meal. And therefore, they get eaten before they reach a specific size and can pass on their genes and so forth. One hypothesis that's been gaining a lot of momentum in the past 6-7 years has been that of oxygen limitation. And by that I mean that as the insects get bigger, as the insects get bigger, they can't get enough oxygen through the body to survive. And this is just briefly the anatomy of an insect. And in nature, the insect is complex, and it doesn't really breathe through little holes called spiracles, which are these highlighted red dots. And these holes take the air in to the tracheal system, which are these highlighted red. And the air then passively flows through the tubes and are then spreading oxygen through all the organs and the internal cellular structures of the insect. So what we're going to do today is to think a little bit about oxygen consumption and how that may affect the possible size that an animal, or insect in this case, an ant can be. And that has to do with trying to calculate how big an ant can get with, and compare the ability of how much oxygen it can take in. Does that make sense? Okay, so Julie's going to take us through.
All right, so we got a little bit of the science, but what we want to think about is using the ant as thinking about the ant body as a structure. And so what are the needs of the structure to survive? So one of the things we're going to do is kind of simplify some of the information. And here's what we're going to do. You're going to actually create something that's going to be a representation of your ant. At your tables, you have some centimeter square paper, and there's information here, and you're going to create a cylinder. This cylinder is going to represent the body of your ant. Okay? Now, a typical ant is about 8 millimeters long and has, if we think of its body as a cylinder, the radius of that cylinder is about 1.5 millimeters. Okay? So since that would be really small, right, you're going to work on a scale, and we're going to do it 10 times bigger. So we're going to make, instead of millimeters, we're going to do centimeters. So you're going to make a small cylinder using your paper to represent your ant. Then what we're going to try and figure out is, can this ant survive? We have some information that we know, and we're going to use that to determine if the ant can survive. So here's what we need to do first. One of the strategies that can be really useful for kids when they're looking at a lot of tests is to help them think about what is this problem about? What are you being asked? So I'm going to hand out this information for you on a worksheet, and then I'm going to ask you to think about these questions before we even move on, just to model some pedagogical strategies, as well as to help us think about what the heck are we doing and why are we doing this. So we'll pass these out. You guys.
So, what do you want to know? We need a better word for that. It's about, they have to go inside. Work. That means you have to work though. Yeah. I've never done this activity. Oh, you haven't? So each thing is individual.
Before you start solving the problem, I want you to take a minute and think about these questions and how your students might approach a task like this. We know that in the Common Core for mathematics, we also know in the Common Core for ELA, there's a lot of information in mathematics. We want kids to persevere, make sense of problems, and I know in science process standards, we need students to do that as well. In the English language arts standards, there's a lot of emphasis on reading informational text. We also know that the first thing most kids do when they see a word problem is sorry, right? So we want to think about how we can help students make sense of a problem like this. So think about the first question without going even starting to solve. What is this problem about? What are you being asked to or what information do you know, and then what are you trying to solve, what are you trying to figure out, okay? So think about those first for a minute. We're going to talk about those first before we actually jump into the problem. So just jot down, you can either turn your paper over to jot down, what's the problem about? Yep.
Question. In part 1, number 2, it says the ant absorbs oxygen at a rate of about 6.2 milliliters per second per square centimeter of exoskeleton. Is that per square centimeter of our scaled up version, or?
No, that's for the size. So that's a really important thing to think about when we're talking about information. Yep. Okay, before we go on, I do want to address these questions, just to make sure everybody is clear on what are we doing and why are we doing this. So what is the problem about? Without numbers, without thinking about the actual task, what are we hearing about in this writing?
Yes. How big can an ant get?
Okay, so we're talking about ants and how big they can get, right? That's what it's about. What's some information that you know? What is the problem giving us?
It's giving us surface area.
Okay, well, it's giving us some dimensions, right? And we can figure out surface area. What else is it giving us? What else is it about providing? Okay, yeah, go ahead.
How much oxygen they absorb and how much they
Okay, so we've got this information about what they need and what they absorb, right? Okay, anything else that we know? They're ants and they're gross, but I guess we need them on some level. Sorry, a scientist would say yes. What are we trying to figure out? Yeah, how big it can get. And we got these two bits of information. One is how much oxygen it needs, how much oxygen it gets. What's the relationship of those amounts for an ant to survive? I mean, should they need more than they get? Should they get more than they need? Which number do we want to use? Which should we pick? Whatever they get should be more than what they need, right? Yeah, so that's what we're trying to figure out. So I'm going to have you guys work on this in your table groups for a while. We'll come back and talk about strategies and ways people are thinking about it.
Well, first thing, one of the things we need to think about is what the actual volume is. And because at the end it says the ant needs 1.5 oxygen. But we're not going to know the second half of the cubic centimeter. So the diameter of what the ants
you're like, wait, which is r squared or diameter or radius? Okay, so don't be shy about that. But I do want to process where people are in about another 5 or 10 minutes.
Okay.
But there's lots of paper if folks want to make more ants.
I got 18
Thank you. Okay, we've been doing a lot of math this afternoon. And we've been finding some different things out about these numbers. And what I want us to do is spend some time to talk about why do people find well, even when you made it with the paper, an 8-centimeter long ant. Some people did that problem. That wasn't the problem I intended, but that was my bad, so I think it's great. That's the problem a lot of people did. So if you made that original ant, and does somebody have an example of it? I think I have one right here. Or, I borrow yours? Sorry, Dave, get it. If anyone just did the strict calculations with this ant, this size guy, what did people find out? It would die. And why would this poor little ant die? Okay. Wouldn't absorb it, it just doesn't have enough, right? Okay. That's an ant that is frighteningly, has a body that's about this size. Not a pretty thought. Did anybody go ahead and work with the ant that's the size, what was mentioned in the paper, an 8-millimeter ant, and find out what happens with that ant? We're hearing different ideas. Is somebody willing to come up and bring their document camera? Is there anybody who's willing to come up? Right? This is the